thanks very much for the introduction. Yes, well, let's get started. I suppose the key thing, the key function I'm going to talk about, or we're going to look at in Haskell, is this interact function that sits inside system I/O. And it takes a function from strings to strings and returns an I/O, something in the I/O monad that does some interaction. And what I want to do is talk through where that idea came from, some of the history of it, and perhaps draw some parallels, draw some lessons from what came out of using that function. If you want to define the system.io.interact function, there it is. It's a two-line definition. What you do is simply get the contents of the file, get the contents of the input, and apply a function to those contents. So what we're doing is taking a function from a string to a string and turning that into an I/O operation. In fact, the previous talk about machines said that this was unsafe and it was, is back in history. But I think there are still some things we can learn from it. And I think there will be some reflections on what was said in that machines talk as well. So, something we teach our first year students. Perhaps we don't put it in this form, but the output of a program is a function of its input, a mathematical function. What goes into the program determines what comes out. And so, for example, you can see on the left-hand side the inputs to a function, and here are the outputs. We're getting a sequence of inputs, and it's giving rise to a sequence of outputs. So there we've got the behavior of the program, but not quite. Because what I've got here is the total input, and what we've got here is the total output. But that's not the full behavior of the program. What determines the behavior of the program is how the two are interleaved. So after a certain amount of input, you'll get this output. And so there's the full behavior of the program, and now we're seeing input and output interleaved. So the interactive behavior of the program is the input-output interleaving. And in the Haskell world, interleaving is what is determined by lazy evaluation. So the lazy behavior of the function f determines the interaction. So you could say the essence of laziness is exposed in this sort of application. Because we're interested to get this interactive behavior, we don't take the full input and get the full output. We take an approximation to the input. The input so far, for example, we don't put any input in at all, and we get some of the output. The first bit of the output says, type something now. And then if we type the string echo, followed by nothing determined yet, we get a bit more of the output. So it's that essential lazy behavior. We're deciding how the program, all the input to all the output, works as an interaction by looking at what the function does on partial data. So it's a perfect example of how laziness is a key. It makes no sense to think of that input-output function as being strict. It is essentially lazy if we're going to play this game. But of course, the problem with that is that it can be a bit complicated, which I will show you. Well, I will attempt to show you. Let's see if I can do this. Oh. So here we are. Is that visible at the back? Are you happy with that? OK. So we can run interact. Oh, what can we do? I've got some examples in here. Oh, where are we? Where's my examples file? Here we are. Here's an echo function I've written up here. It takes the input there, y's, and we get the output begins with a prompt, and then we take the head of y's, and then we put a new line, and then we get the tail. So let's see what we get with this. If we do interact, oh no, I need to load it, sorry. I know it's after, so this is a nice after lunch talk. It's relatively slow going. I'm showing you some examples. Sorry, that's at the bottom. But let's try, what should we try? Let's try interact. what's it called? N echo. What's it do? Prompt, W. Oh, we collect W back, E. We're getting this sort of behavior. We're getting each character we type in, the character's echoed immediately, we get back the prompt. We could try now. This implementation of interact is not a terribly nice one, because when I interrupt it, it kills GHCI. It's a nice, if somebody would like to change the REPL on GHCI to make this work properly, that would be a nice thing to do. Okay, so let's try, instead of echo, let's try this other one. Oh, sorry, yes, you're quite right. Oh, yeah. Now we didn't get the, we get the prompt after we type the input. So you can see we're getting this. Whereas if you look at these two functions, just to make the point, if you applied these to a list that is properly terminated, their behavior is exactly the same. But the fact I'm taking the head here and doing a pattern match here means that their interactive behavior is quite different. So if you want to use this sort of paradigm to write interactive programs, it's going to be quite tricky. But we can do some nice things. Let me show you one example that is nice. If I can get this, let's remind ourselves. We could do something like this. We could do, if I could type it. Sorry, this is backwards because it's a composition. What we're doing here is we've got a nice stream processing function which is splitting input into lines, mapping reverse along the input, and then producing the output. Oh, if we interrupt that. And I'll just show one more example. Oops, no, I didn't need to do that, sorry. I have to do two. I have to get the load, so there we are. What do you think will happen if I do this? What if we map ID there? We thought what we were going to get was split into lines, produce each line, and then get the lines back. What it's doing, in fact, is echoing character by character. So again, the laziness interacts perhaps badly here with whether you're treating the input as raw or buffered. So it's a bit of a nightmare, I suppose, is one way of summarizing that part of the talk. So we've seen those examples. Let's build a model of interactions and see how they combine together. So that's what we'll do. And now why this is back to the future, and here I guess I reveal where this came from. In 1987, there was a year of programming at the University of Texas. Tony Hoare and Dijkstra were there, and they did 6 institutes through the year, and there was one on lazy functional programming. And this work was presented at that. So it's interesting to think that many of the ideas we're looking at now have been in the air for a long time. You could argue that they predate what was going on at that institute anyway. So we had a number of us were there. We provided an introduction to lazy functional programming, looked at several case studies and so on. And so we covered an awful lot of stuff. There's particular enthusiasm among the University of Texas graduate students who were there. They said, we want to make functional programming a more visible priority in the department through recruitment of faculty engaged in research in the field. Not sure they've done it yet, but lots of other places have. Interesting to get that historical perspective. And there's a book, if you're interested in following this up, there's a series of books on this. It's David Turner who ran that particular institute. So the question is the work that was done then, does it still make sense? It was what we were thinking about 30 years ago. Does it still give us a sensible view of what's going on now? We can think about how to bring it up to date. And are there any missed opportunities? Were there things we missed? Are there missed opportunities in what we did then? Now, of course, Haskell didn't exist in 1987. You could argue perhaps this institute and the fact the work was done in Miranda was one of the reasons Haskell was invented as an open source alternative to Miranda, which was a commercial product. So in taking the work from then, I had to transliterate it from Miranda to Haskell. And in the repo, you can see I've got some notes on what transliteration I had to do. But it's all very low level, nothing terribly complicated. And on top of this, I did some work on building a formal model of interactions. We did so, and that work is still sitting there. So this is the model. And it's interesting to compare this with the sorts of abstractions that were being presented within the machines lecture this morning. It's a relatively simple model. You can view this in two ways, this type. In one, you've got a model of functions with functions which have I/O side effects. So viewing it horizontally, what you've got is a functions, but something happens as that function is evaluated. The other way of viewing it is to sort of view it vertically as something interactive, but as part of the interaction, a state is changed. And the state can not only change value, it can change type. So we might start off with something of type A. At the end of the interaction, we have something of type B. So we've got that general model. And so there's two separate views, depending on whether you see it as an arrow going top to bottom or going left to right. And here are the definitions in Haskell. We've got that type of interactions. Conditions are a similar analogous type. And then, what's nice about these things is you can put them together in all sorts of different ways. We've got that picture for interaction. We can wire these things in sequence. We can wire them in parallel. We can build loops. We can do alternatives. We can pass values through. And the model that was around then had all these things in it. And all these things can be given a definite type. So you can imagine here, if you pass in an A and a C, you'll get back, say, a B and a D paired together. Here you're sequencing. And so on. So we can build these combinators. So what we built was a little language for describing, a combinator language for describing interactions. And the key combinator is this one for sequencing, as you might imagine. I'm presenting this in this way because this was how I found the code when I dusted it off and transliterated it. We're taking an interaction that from, if you like, a side effecting function from A to B and a side effecting function from B to C, and we're sequencing them together. We're composing them. What do we do? Well, we apply the first interaction. We gather what remains of the input, the change state, and the beginning of the output, and then apply the second interaction and somehow add the output to that, what comes out of the second interaction, and make output I'd written just as this function. I got this functional abstraction here. I could have written it as two clauses in the where. So I transliterated this, and it failed. Any thoughts about why this isn't going to work? Why does this fail in Haskell?
Strictness problem?
Strictness, well, yes. There's pattern matching on it, yeah. So what Haskell has a slightly different view of pattern matching than Miranda had. This pattern, putting the tilde in front of that, makes the pattern irrefutable. It can't fail, and so it makes it more lazy. The point is that without the tilde in here, this function you can't make the operational step of going from the left-hand side to the right-hand side without having a tuple there. If you put the tilde in front, you can make progress to that immediately, and what effectively you do in here is you have selectors on that tuple, which get applied later. Now, of course, this is precisely this sort of nonsense that you have to get right when you're thinking about putting together these lazy. So if we add these two irrefutability marks, the code will work. But when I last talked about this, Neil Mitchell very kindly reminded me that Haskell doesn't get it all wrong. We need to make this irrefutable, but in a binding of a pattern. Pattern bindings are by default irrefutable. So we can take that out, and then it will work. But you can see this is where, I said this was about the essence of laziness. It really is about getting these done. It's about how it behaves when you don't have all the information you might want. And when you've got it, it's fine, it works. So sequencing is, as if you like, the key combinator there. And then you've got alternation, which you just apply the condition, and then the condition takes the state. The conditions are assumed not to side effect. I mean, we had that type definition earlier. And then you get this nice sort of behavior that you can define the behavior of a while loop as this recursive value. We've got this recursive value inside this interaction type. So y is alt cond, do the interaction and then do while again, or null. So we get that nice top level definition there. So we've got those combinators. And then there was this one, which looks a bit weird. But those of you with sharp eyes might think, this looks familiar. This looks like... this is the equivalent of bind, before bind was around. Because somehow the idea was you had to, and there's a generalized version which makes probably more sense. You get this, as a result of your first interaction, you get a value, and you want somehow that value to determine what happens next. And that was, I called it passing parameters. But I mean, it fits into this behavior quite happily. You get the new state back from here, and you just apply it in that clause. But it was this rather odd. So it was here you could begin to see a bit of this monadic stuff appearing. And there's some primitives. You get a primitive which is map, effectively, and you get writing and reading, and some other things like forgetting the state and starting with a new state and changing state and waiting. And then you've got to write a function that will actually do the running, which we can do in a Haskell form. So we've got enough primitives to get things going. And here are the definitions. I mean, there's nothing terribly interesting about them. There's a write is you just stick something in the output. Read, you take the head of the input. Apply, you apply the function, so it's mapping. Here you can do run through and interact. You take the full input. You split it at whatever points you want to split it at, and run it in that way. So entirely straightforward. And I can show you some stuff in action there. Actually, what I'll do, let me show you some examples, and then I'll show you the stuff in action. So here's a function that copies input. While true, read in a line, and then sequence with writing out the identity. What you can see, this is imperative style. What you can see here, this is like a little language for imperative programming that we've rendered into combinators. Or you can write it like this. You can say copy is you read in, then you write out, and then you copy again. So what we're doing there is pulling in some of the features of the host language to give us some meta-circularity. So we're using recursion in Haskell to give us this recursive program, this recursive imperative program. So you could see, even then, you're getting different styles of program. Imperative, pretty, if you like, a shallow embedding of a an imperative language, and here you've got a bit of meta-circularity. Actually, no, I'll come to this one. Let me show you some examples then. How are we doing for time? Okay, we're doing fine. Let me just. So we've got some examples in here. Which were the things? I got those copy functions in here. Yeah, here we are. So there you've got this recursive copy function read in. Let's just check that works. I'm sure you, I mean, I don't have to show you that these things work, but it's. So what we want to do is run copy, and what we need to do here is we have to give it a starting value, but as it's taking, we have to give it, because it's an interaction that starts with a state and terminates with a state, we have to give it a starting value for that state. In this case, it's just the null value. There we're getting that copying done, and we're getting this from the recursion in there. So what we've got is a tractable way of writing these programs. So what effectively we're doing here is a small API. And I was struck by the talk about machines as to how complex it is to define a good API. And you could argue that the API that I produced here was not perfect. And one of the things that has changed in the last 30 years is that we've got better in some ways at designing APIs, but perhaps in others we've just got more complicated and perhaps not better. So there's an example of two sorts of copy function in this style. I think this shows us one of the disadvantages of this approach. What's going on here? This is a function that will take an integer, and then it will add up that number of integers. So if the first input is 5, it will then collect 5 integers and give you the result. Now this approach, as I said, you can have a state which changes at every step. So we start off with a state that just has the counter in it, and then after one step we've got a sum because we've added a value to the right. And then we carry on with that, and here we add a second value. This is our accumulator here. Oh no, this is our... Oh, this is our, yeah, this is our oh, that's passing on the, yeah, that's just an artifact of this. So this explicit wiring you've got of adding values to the right, adding a value to the state, adding a value to the left, is a nightmare in practice. Getting this right is really not terribly nice. So what you want to do instead, if you take this model, is you have an abstract state with accessors and mutators and so on. And if you do that, you finish up with a state that has accessors and mutators for things like the counter and the sum, and you get a very nice imperative style of programming there. What else can you do? Alternatively, you can use this sort of more synthetic approach and say, what we want to do is get a number, and then with that number, build ourselves a program. So this is highly reflective. What we're doing is we're saying, start off, collect a number, and then using that number, we replicate add num together n times, and then finish. So we add a number to the state n times. So what we've done here is using this sort of binding mechanism, we've effectively synthesized a program. We don't deal with an object state. We have a sort of meta-level state that builds the program for us. So that's sort of the style that we've got. And let me just quickly demonstrate that. Where are we? So let's interrupt that. Go back into GHC, load the examples, and then we can look at, where have we got it? Collector. There's a whole set of examples in here, and you can grab them on the, oh, here we are, it's collect nums. You can grab them off the off the GitHub repo. I'll put the link for that later on. So what we want to do is run collect nums, and what should we do? Let's start with 0. And let's say we want to collect 3 numbers, so we'll collect 2 and 1 and 67, and we get back the answer 70, and this bit of the interaction is terminated. So you can see that we're getting the behavior we would expect to get. Let's start this again. So looking back, what have we got? Well, we've got everything that we use now in writing Haskell programs. Higher order functions we used, lazy evaluation, pattern matching, algebraic types. So all that stuff was there, and people were programming with this stuff quite happily to build this sort of model and build the API on top of it. Well, they were almost all there. What wasn't there? Miranda didn't have a lambda or a let, so every function you wanted to talk about had to be named, and that's not a very nice style. If you've got lambdas, you find thinking of names for things which are effectively anonymous functions is not very useful. It makes programs harder to read. So having lambda improves things, and I think having let, Miranda you could only use where. There wasn't a let at the expression level. So you finish up with a variant of a point-free style with too many names around. It didn't have any sort of class mechanism. So that has the advantage of giving you very nice type errors. You don't get the problems with type classes, but you don't have overloaded operations over numbers or anything else. So that's a limitation. But I think the thing that shows up most from this is that there were no design patterns. You know, this was structured around this idea of a function that might have side effects, or something, or an input-output operation where you could potentially change the state. But the model mixes aspects of monads. You can see that in pass parameter. Arrows, where you were passing values around an interaction. That's a classic sort of arrow interaction. And there are applicative aspects in there as well. Now, it's interesting. You could argue that maybe what you have there is the right abstraction because you weren't, the design wasn't influenced by having any of those particular templates imposed on what was going on. It's very difficult to know. It could be that, but it could mean if you say, let's make this monadic, then the behavior is simpler. But it's interesting, if you look at the type, the interaction type has 2 parameters. It has an input type and an output type. That's difficult to model monadically in a simple way. So that does restrict, gets rid of this model where you can easily change the type of the state at each stage in the interaction. And it also makes things like these passing values around rather more difficult to handle. Now, I guess what it forces you to do is to perhaps this model where you have an abstract state with accessors and mutators and so on, and you just use that abstract state for the whole of the interaction. But these are clearly things that are not 30 years old. These are things that are now shaping what programmers do in a way that just taking the raw materials of higher order functions, data types, lazy evaluation didn't do. So I think we've got new tools, and it will be interesting to see how those tools shape what we do. I think we understand how monads shape what we do. I think arrows have shaped some things. I was talking to Graham over lunch. How applicative will shape what we do is perhaps less clear in general. And just one more point to make about this. I think designing APIs is one of the things. Haskell makes it easy for us to build complicated models of the world. And you look in Hackage and so on. And there's a huge There's a plethora of interesting abstractions. I think there are many fewer usable abstractions than there are interesting abstractions. I think we have a problem at designing things at the right level of generality, I think. I mean, some libraries are so general that they're very difficult to use because there's not enough specific in them. And some are more general than they need be to do a small collection of specific tasks. I think, and this is an argument people make in OO programming, it's very difficult to design classes in OO and class hierarchies. I think we perhaps pay too little time in Haskell to thinking about designing good APIs. I mean, you look, for example, at, maybe this is not such a good example, but you look at the number of different libraries there are to do generic programming. If we got it right, there'd be one library, I think. And perhaps the same with modeling state machines and so on. But there are a number of different libraries. Okay, there is a space. Perhaps there's room for 2 or 3 abstractions, but there isn't room perhaps for 12 or 13. Anyway, enough of that. You can see this as a shallow embedding of a language for interactions. What we're doing is representing the while construct as a combinator. But you could do this as a deep embedding. You could say, here's a data type that represents the sorts of interactions I was describing. And then you can write an interpreter in Haskell, and that's clearly something, beginning to have a DSL which embodies the sorts of interactions we're trying to design. And then you can write an interpreter for that, but you can also write things that will normalize, will optimize, and so on when you have an explicit representation of the program. So that's something that we are doing in Haskell, which we weren't doing that number of years ago. Of course, it hammers the type system. You would probably like, if these interactions have a state in them, you would like to reflect that state in the types of the interactions, and then you're going to have dependent types. Sequencing is going to be a dependently typed operator. So getting the type system to reflect accurately what's going on in the language you're representing is tricky. But I think clearly types have grown. We've got GADTs, and they get us some way towards dependency. But maybe we need full dependency if we're going to do the proper thing with representing things as DSLs. The other thing that springs to mind is that it would be very nice if somebody brought fudgets back. Fudgets were the only true declarative GUI component that I was aware of. And they were used in anger to implement one of the predecessors of Agda had its GUI interface built using fudgets. It's a very nice library by Thomas Hallgren, built, I guess, probably 20 years ago, and used in the early 2000s for building responsive, entirely declarative GUIs. So I think that would be it would be nice to see those coming back. You can see there's a model of of how they were designed just at the bottom of that page, and you can see there's a link there to the page. So I think the language has not changed. The basic constructs we've got, higher order functions, data types, laziness, they're all the same. But I guess where things have changed in the last 20 years or so is building libraries, building APIs, tools. They were still talking a lot about what are the right tools for developing Haskell programs, interoperability and so on. So a lot of the things around the language, and I think particularly the community. I mean, it's extraordinary to come to a meetup like this and have so many people excited about Haskell. And I think that's a great, it's a great pleasure for somebody who's been talking Haskell at much smaller audiences over the years. And I think it's, to conclude, I'd say there are a few things that haven't happened. I think 30 years ago, people thought we routinely prove our programs correct. That was an assumption. You know, it would be by 2017, all programs will be proved correct, and especially functional programs. That was one of the great things about functional programming. Maybe we're getting close. And perhaps what we're seeing now is that verification doesn't mean proving correct any longer. It means using things like liquid Haskell, it means doing restricted model checking, and so on. So perhaps we took perhaps a rather naive view of the world. I think people thought compilers would be derived from semantics. You know, there was Yak. Yak took the lexical aspect and the grammatical aspect and gave you a lexer and a parser. With an attribute grammar, you could describe the type checker. With an attribute grammar, you can also describe all the static semantics and so on. But that, I think we're still... I said to our compilers class, nobody writes a parser by hand. And my colleague who was in the lecture said, yes, they do. Nobody uses Yak in anger. So people are still writing parsers by hand, but we're certainly no way close to having compilers derived from semantics. The buzz around functional programming was, in the 1980s, was that we were going to get special purpose parallel hardware, general purpose sequential machines were going to come to a halt. We're going to have special purpose parallel hardware, and that was where functional languages would score. Well, it didn't work out like that, but ironically, we're getting close to that again. And the other thing that people talked about was the end of the program as text. Programs aren't going to carry on being text. It'll be these complicated semantic things that we'll manipulate. Oh no, they're not. They're still text files. And if you want to build tools, that's a bit of a nightmare. So a number of things that people thought would happen haven't, but you know, other things have evolved in quite different ways, I think. Okay, so that's where my slides are, and oh, sorry, I put that, and this is where the presentation will be. But that's where my slides and the code from this talk are up there on GitHub. So, any questions? Thank you very much.
I'll jump in with a question.
Yeah.
So towards the end, you kind of suggested that we should be designing APIs for what they do rather than based on prior existing type classes or something like that. But that interact one could certainly be a monad. Is it worth kind of then going back and seeing what you've got at the end of your kind of API design and seeing how it fits in with existing Haskell nomenclature?
I mean, yeah, that's something one could do. But as I say, it would be limited because the interactions at the moment, you can have an input state which is an A and an output state which is a B. So it's parameterized over two types. Yeah. It could be an arrow, yes.
Well, I also noticed though that there was the one program you demonstrated where actually having that state changing was complicated.
It was, so you could argue that. So it could be a monad, it could be an arrow. Mm-hmm. But which is right?
Right.
That's the... No, I think it certainly is. It smells more of arrows with these passing the values around. Okay, and is that an arrow as well as a monad? So it's interesting. So I'm not sure whether these things are helping us or hindering us. You certainly get the do notation if you have monads, and that's a clear plus. Yeah, I mean, it's interesting that, and I suppose I'm quite pleased applicatives have come along and said, well, not everything is a monad. And arrows came along and said, not everything is a monad. It is, I think we tended to be, I think there's been a period when everything people have thought everything must be a monad. But a relative monad, I'll think about that. And that's parameterized over two? Huh? Okay. Okay, and I guess you could stick the do notation on top of. Interesting. Okay, but I think it's intriguing. I don't know. I think we're at an early stage of thinking about how to design these things right. And Yeah, but maybe you're right. Maybe what I need to do is sit down and say, this is the monadic version, this is the arrow version, and see what it is. It could be an interesting exercise. Thank you.
Okay, well, if there's no more questions, let's thank the speaker again.
Thank you.